Here are the top 10 most important things you need to know about vectors. Must know number 1. What is a vector? Let me start by explaining to you the difference between a scalar and a vector quantity. A scalar is a quantity that has magnitude only. Examples of scalar quantities are things such as temperature, mass, volume, and speed. On the other hand, a vector is a quantity with both magnitude and direction. Examples of vector quantities are velocity, displacement, and any force, including the force of gravity. Now let me show you how we represent vectors. Vectors are represented as directed line segments. And there are a couple different ways to name this vector. We could choose a letter. I'll choose the letter V, and then put a vector symbol above it. Or we could choose a letter for the start of the vector, and the start of the vector we call the tail. I'll choose the letter A for the tail of the vector, and put another letter at where the vector finishes, at the tip of the vector. I'll choose the letter B. And because this vector starts at A and finishes at B, we could define this as the vector A, B, and then put a vector symbol above those two letters. That communicates that we have a vector that starts at A and finishes at B. Now this vector has both a magnitude and a direction. Its magnitude is represented just by the length of this line. And if you put vertical lines around the name of the vector, that means the magnitude of the vector. The direction of this vector is communicated by the arrow that's at the tip of the vector. That shows what direction it's going in. And there are a couple different ways to communicate the magnitude and direction of a vector. Let's say this vector represents a velocity. We could say that the magnitude of this velocity is, let's say, 10 kilometers an hour. And we would have to give it a direction. We could give it a direction based on its quadrant bearing. I could say that it is north 37 degrees towards east. That means it's moving towards north, but moving 37 degrees towards east. Now, this isn't the only way to define both the magnitude and direction of a vector. To describe how to get from the tail to the tip of a vector, we could instead break the vector into its horizontal and vertical components. By doing that, we get a vector in what's called component form, and we call that type of vector a Cartesian or algebraic vector. Let me make up a new vector. I'll call it vector u, so I can show you what component form looks like. Inside of square brackets, I write a horizontal and vertical component of a vector. So the 5 is the horizontal or x component of this vector u, and the 2 is the vertical or y component of this vector. To graph this vector, on a Cartesian grid, I choose a starting point. I'll choose right here at the point 2, 2. And then to get from that point to the tip of the vector, I have to move 5 units in the x or horizontal direction, and then 2 units in the y or vertical direction. And that would bring me to the tip of the vector right there. And then this vector u could be translated anywhere on the Cartesian grid as long as I keep its magnitude and direction the same. So what's commonly done is it's drawn in what's called standard position. And that means it's drawn so that its tail is right at the origin of the Cartesian grid. And we do that because if we look at the coordinates of where the tip of the vector is, it's at the point 5, 2. Notice those coordinates exactly match the x and y components of my vector. And then if I wanted the magnitude of this vector u, if I were to label the horizontal and vertical components of this vector, you would see that what we have here is a right angle triangle. So to find the magnitude of vector u, I know that 5 squared plus 2 squared would equal the magnitude of u squared based on Pythagorean theorem. And if I rearrange that, I would know that the magnitude of u equals the square root of 5 squared plus 2 squared, which is equal to the square root of 29. And it might be useful if I give you a generalized formula for the magnitude of any vector. Let's say we have vector u and we want its magnitude. What we do, based on Pythagorean theorem, is we do the square root of the x component squared plus the y component squared. Let me make up one more vector to try this all out. Let's say we have another vector, I'll call it vector k, and it's the vector -2, -4. To draw this vector, I could draw it in standard position by putting its tail at the origin and making the tip go to the point -2, -4. And then if I wanted the magnitude of this vector, if I follow my magnitude formula, I just have to do the square root of the x component squared plus the y component squared. So that would be the square root of 20, which would simplify to 2 root 5. Must know number 2, vector addition. Let me start by showing you how to add two vectors geometrically, and then I'll show you algebraically after. Let's say we're given two geometric vectors. I'll draw directed line segments for vector A and vector B. Let's say our goal is to find what vector A plus vector B looks like. The sum of two vectors is called the resultant vector, and that just means we want to find the net displacement caused by these two vectors. And to visualize that, what we need to do is reposition these vectors without changing their magnitude or direction so that they're placed tip to tail. So I'm going to move vector A and vector B so that the tail of B is at the tip of vector A. And I'll center this. And now that they're positioned tip to tail, to find the resultant or the net displacement caused by these two vectors, I draw a vector that goes from the tail of my first vector up to the tip of my second vector. So this is vector A plus vector B. Whether someone went from the start to here and then from there to there, or if they started here and just went straight up to here, you would have the same net displacement. That's why this blue vector represents the sum of vector A and vector B. And now let me show you how to add vectors algebraically. Let me give you two vectors in component form. Let's say we have vector A, which is the vector 1, 3, and vector B, which is the vector 2, 2. To add these vectors algebraically, all I actually have to do, to find vector A plus vector B, my resultant is going to be a vector that has both an x and a y component. To get the x component of my resultant, I just add the x component of vector A with the x component of vector B. And to get the y component of my resultant, add the y component of A with the y component of B. So when adding the x components, that would be 1 plus 2. And when adding the y components of the vectors, that would just be 3 plus 2, which gives us a resultant vector of 3, 5. Now let me show you on this Cartesian grid why that works. If I were to draw a vector A, which is the vector 1, 3, and to draw a vector B, which is the vector 2, 2, now when adding vectors, they have to be placed tip to tail, so let me take this vector B and reposition it so that its tail is at the tip of vector A. And I know the resultant would go from the tail of the first vector to the tip of the second vector. And I notice the tip of this vector is at the point 3, 5, which corresponds to our answer here. And it should be easy to see why that works. Let me zoom in a little bit. The x component of my resultant we know is 3, and the y component is 5. This 3 is just a sum of the x components of vector A and vector B. Here's the x component of A, and here's the x component of B. Notice combining those together gets me the x component of my resultant vector. And then also here's the y component of A, and here's the y component of B. Combining those together, you can see that that corresponds to the y component of my resultant vector. Must know number 3, vector subtraction. Let's say we're given two geometric vectors, vectors A and vector B. Let me show you how we can draw what vector A minus vector B looks like. There are two main ways to do this. Method 1 is by using your knowledge of vector addition to add the opposite of vector B. And what I mean by that is, if we're interested in what vector A minus vector B is equal to, algebraically you would know that that would be the same thing as doing vector A plus the negative of vector B. Adding a negative is the same as subtracting. And we know how to do vector addition. We reposition them tip to tail, and then draw the resultant of the two. So let me draw vector A and the negative of vector B tip to tail. So I'll redraw vector A by keeping its magnitude and direction the same. And to that vector, I have to add the negative of vector B. Well, the negative of vector B would have the exact same magnitude, but would be going in the exact opposite direction. So I'll take this vector B, and I'll switch it to the negative of vector B by putting the arrow at the other end of the vector. And now this is the negative of vector B. So if I want to add those two vectors together, I just have to position them tip to tail, and I know the resultant vector is going to go from the tail of the first vector to the tip of the second vector. So there's what vector A minus vector B looks like. The other method for getting this exact same vector is rearranging our problem into an addition problem, and we use the triangle law for this. Now I know if I want vector A minus vector B, that's going to result in a new vector. I'll call that new vector vector C. And then rearranging this equation to isolate A, I can move this to the other side to make it plus vector B. I get vector A is equal to vector B plus vector C. This will all make sense once I take these two vectors and reposition them so they're tail to tail with each other. This statement says that vector A is a sum of vector B and vector C. Well, that would mean that vector B plus some other vector would equal vector A. So I'll draw that other vector and call it vector C, right? Vector B and vector C are tip to tail with each other, and the resultant of those two vectors is supposed to be vector A. But remember, this vector C is actually equal to what vector A minus B is. And if we compare these two vectors, this one and this one, you'll notice they have the exact same magnitude and direction. Now, to use this method, there's actually a shortcut. We don't have to do this rearranging algebraically each time. To subtract two vectors, you just place them tail to tail, and I know the difference of those two vectors will connect the tips of the two vectors. And because we're doing A minus B, the first vector in the subtraction is A, so vector A minus B will have its tip pointing at the tip of vector A. Now that you know how to subtract vectors geometrically, let me show you algebraically how we subtract vectors. So I'm going to move this over a bit. And let's say you are given two algebraic vectors. Vector A is 6, 3, and vector B is 4, negative 2. Then let's determine what vector A minus vector B is. If I want to do vector A minus vector B algebraically, I know my result is going to have an x and a y component. To get the x component, I do the x component of A minus the x component of B. And same thing for the y components. The y component of A minus the y component of B. So applying that to this question, vector A minus vector B, let me just rewrite the vectors in this subtraction. So that's the vector 6, 3 minus the vector 4, negative 2. And then to get this vector A minus B, to get the x component, I just do 6 minus 4. And to get the y component, I just do 3 minus negative 2, which that would simplify to the vector 2, 5. Must know number 4, scalar multiplication. For this, let's look at what happens if we were to take some vector and multiply it by a scalar. So let's say we have k times vector A. When multiplying a vector by a scalar, it might get longer or shorter depending on the value of k, but the result will always be a vector that's parallel to the original vector, either in the same direction or the exact opposite direction. If k is bigger than 0, then k times vector A is going to be in the same direction as vector A, and with a magnitude equal to k times the magnitude of A. But if k is less than 0, so if it's negative, k times vector A is in the opposite direction as vector A, and its magnitude is equal to the absolute value of k times the magnitude of A. And the best way for me to clarify what this all means to you is with an example. So let's say we have some vector, vector u, that is pointed straight up to the north, and its magnitude is 10 kilometers an hour. Let's draw what negative vector u, a half times vector u, and negative a half times vector u look like. So let me start by drawing vector u. If I want to draw a negative vector u, that meets the criteria of the scalar being less than 0. Our scalar multiple this time is negative 1. So negative u is going to be in the opposite direction as vector u. And its magnitude is equal to the absolute value of k, well, the absolute value of negative 1 is 1, times the magnitude of A. So its magnitude is just being multiplied by 1, so the magnitude is not changing, but it will be going in the opposite direction. So this is the negative of vector u. It's 10 kilometers an hour south. A half times vector u, well, that has a positive scalar, so it's going to be in the same direction, and its magnitude is going to be a half times the magnitude of the original vector, which means instead of 10 kilometers an hour north, it's going to be 5 kilometers an hour north. So I need to draw a vector that is half as long, but pointing in the same direction. And lastly, negative a half u is going to just be the exact opposite of a half u. So it's going to have the same magnitude as a half u, but in the opposite direction, which means it's going to be going 5 kilometers an hour south. So hopefully you can see how scalar multiplication works. Let me show you algebraically how we can do it as well. So let's look over at this Cartesian grid. Now let's say we're given vector A in component form is the vector 2, 3. Let's determine what 2 times vector A is. Algebraically, this calculation is quite easy. 2 times vector A would just be 2 times the vector 2, 3. And to do that calculation algebraically, we just have to multiply both of the components of the vector by the scalar that's in front of the vector. So this would equal, I multiply the x component by 2, which is 4, and I also multiply the y component by 2, which is 6. And now let me show you on this Cartesian grid how vector A and 2 times vector A compare to each other. So if I were to draw vector A, I'll start its tail at the origin and put the tip at the point 2, 3. And drawing 2 times vector A, its tail is at the origin and the tip is at the point 4, 6. Notice both vectors are going in the same direction. That's because the scalar is positive. And 2 times vector A is double the length of vector A. Now, one useful application of scalar multiplication of a vector is creating something called a unit vector. So I could create unit vector A, and I could communicate that by putting this little hat above A. That means unit vector A, which means a vector that goes in the exact same direction as A, but it only has a magnitude of 1 unit. So how could we shrink this vector so its magnitude is only 1 unit? Well, we just have to multiply that vector by 1 over its own magnitude. And if I want the magnitude of A, I know it would be equal to the square root of the x component squared plus the y component squared. So 2 squared plus 3 squared is 13. So the magnitude is the square root of 13. If I multiply that by vector A, what this scalar does to this vector is it shrinks its magnitude down to a magnitude of 1, but it keeps it going in the same direction. If I were to multiply both of these components by 1 over root 13, the approximate values of that are 0.55 and 0.83. If I were to draw that vector, let me zoom in, it would be this vector right here. It's in the same direction as A, but its length is only 1 unit. Must know number 5, dot product. Dot product is the first of 2 special products you can find with vectors. Dot product is sometimes referred to as a scalar product. And that's because the result of a dot product is always going to be a scalar. Let's say we're given 2 vectors, vector A and vector B. The dot product of these 2 vectors is the product of the magnitude of one of the vectors, we'll say vector B, with the magnitude of the part of vector A that is applied in the same direction as vector B. So let me show you the formula that does this product. A dot B, based on the definition, is a product of 2 things. The magnitude of one of the vectors, we chose vector B, so I need to do the magnitude of vector B and multiply that by the magnitude of the part of vector A that is applied in the same direction as vector B. To visualize that, let me break up vector A into 2 vectors. One vector that's parallel to vector B and one vector that's perpendicular to vector B. Now we actually only want this one that's parallel to vector B. So let me erase this other one. But I'll put a dotted line where it was, so you can remember how we created this bottom vector. And there's going to be a 90-degree angle between those lines. This vector down here that shows the part of A that's going in the same direction as B, we have a name for that vector. Let me zoom in a bit. That vector is called the projection of vector A onto vector B. So based on the dot product definition, I need to multiply the magnitude of vector B by the magnitude of the projection of A onto B. And if we know this angle between vector A and vector B, and we know trigonometry, we should be able to come up with an expression for the magnitude of that projection. So if I want the length of this side of this right triangle, I can just use SOHCAHTOA. I know that cosine of this angle would equal the magnitude of the adjacent side divided by the magnitude of the hypotenuse. And then rearranging this to isolate the magnitude of the projection, that would be equal to the magnitude of A times cosine of theta. So in my dot product formula, I can replace this magnitude with the magnitude of A times cos theta. And that's the dot product formula for if we have geometric vectors where we know both of their magnitudes and the angle between the 2 vectors. If we're given the vectors in component form, so if we're given algebraic vectors, the formula for finding the dot product is to just multiply their x components plus multiply their y components. So those are the 2 formulas, and you can decide which one to use based on whether you have geometric or algebraic vectors. And I should mention one more thing. We know that dot product is a scalar product, but that scalar product will sometimes be positive, sometimes negative, and sometimes will actually be 0. And that will all depend on the angle between the vectors. If the angle between the vectors is less than 90 degrees, like in the diagram that I have here, well, I know cosine of an angle less than 90 is positive, so the dot product will be positive. If the angle between the vectors is bigger than 90, let me actually just do a rough sketch of what that would look like. Cosine of an angle between 90 and 180 is negative, so I know the dot product in this situation would be negative. Another way to understand why the dot product is negative when the angle is bigger than 90 is because if I were to draw the projection of A onto B in this scenario, notice it would be going in the opposite direction of vector B. And the third and final scenario is if the angle is equal to 90 degrees. If the angle is equal to 90 degrees, we will be doing cosine of 90, which is 0, which means the dot product is going to be 0. And if I were to draw two vectors that have an angle of 90 degrees between them, if I were to try and draw the projection of A onto B, I wouldn't be able to draw a vector that has any magnitude. It would just be the 0 vector, which means that this product would become 0. Let me now do two quick examples of calculating a dot product. Let's look at this first example that I drew. I've given you two geometric vectors and asked you to find their dot product. Based on the formulas that we found earlier, the dot product of geometric vectors is this formula. I just multiply their magnitudes and then multiply that by the cosine of the angle between the two vectors. So for this question, I would say that A dot B is equal to the magnitude of A, which is 20, times the magnitude of B, which is 30, times cosine of the angle between the two vectors, which is 40 degrees. And if I do that calculation, it's approximately 459.6. Now remember, what did this calculation actually find the product of? We actually found the product of the magnitude of one of the vectors, let's say the magnitude of vector B, with the magnitude of the projection of vector A onto vector B, which would look like this vector right about here, which is parallel to B, and would form a 90-degree angle right here when connected back to the tip of vector A. And now let's do an example for algebraic vectors. Since I'm giving two algebraic vectors in this example, I can use this formula to find their dot product, where I find the product of the x components, the product of the y components, and then add the results. So for A dot B, I multiply the x component of A by the x component of B, 5 times 4, plus multiply the y component of A by the y component of B, negative 3 times 7. This gives me 20 plus negative 21, which is negative 1. So the dot product is negative 1. And because that dot product is negative, I know that the angle between the two vectors must be bigger than 90 degrees. Must know number 6, cross product. This is the second type of product you can do between two vectors. This cross product is sometimes referred to as the vector product. And that's because when you cross product two vectors, your result is a vector. So if you do vector A cross vector B, you get a new vector, we'll call it vector C, where vector C is perpendicular to both vector A and vector B. And also the magnitude of vector C would be equal to the area of the parallelogram formed by vector A and vector B. So let me draw two geometric vectors, vector A and vector B, so I can help you visualize what this means. The most important part of cross product is that it generates a vector that is perpendicular to both of the original vectors, and the only way that could happen is if we work in 3 dimensions. Anything that lays on the same plane as those two vectors can't be perpendicular to both of them. So in order to draw the cross product vector, I would have to draw a vector that is perpendicular to the screen that you're looking at. I'll do my best to depict that on this flat surface here. If I say this is vector A cross B, that would mean that if I zoom in here, it forms a 90-degree angle with vector B, and it also forms a 90-degree angle with vector A. And in order for that to happen, this vector would have to be coming straight out of the screen at you. And we communicate that by saying vector A cross B is coming out of the page. Now I know it's coming out of the page and not going into the page because of the right-hand rule. The right-hand rule says lay your right hand along the first vector that's in your cross product and curl your fingers towards the second vector that's in your cross product. And then your thumb will point in the direction of the cross product. Therefore, A cross B would be going out of the page. But if you were to try to do B cross A, you'd have to lay your right hand along B and then try and curl your fingers towards A. In order for that to happen, you'd have to flip your hand upside down and your thumb would be pointing into the page. So B cross A would be in the exact opposite direction of A cross B, but it would have the exact same magnitude. So the order of cross product is important because you can see you get vectors that are opposites of each other, depending on whether you do A cross B or B cross A. And then another part of the definition of cross product is that the magnitude of the cross product is equal to the area of the parallelogram formed by A and B. So let me roughly sketch that parallelogram. And then the area of this parallelogram is equal to the magnitude of A cross B. So how would I find the area of this parallelogram? Well, the area of a parallelogram is just its base times its height. So what would the height of this parallelogram be? Let me just turn this into a little right triangle here and label this as the height. If I knew the angle between the two vectors, based on SOHCAHTOA, I know that sine of the angle would equal the opposite side over the hypotenuse. And then if I rearrange this formula to isolate h, I can see that the height of the parallelogram is equal to the magnitude of b sine theta, which means the magnitude of the cross product of A and B would be equal to the base, which is the magnitude of A, times the height, which is equal to the magnitude of B times sine theta. So that gives you the magnitude of the cross product. But if we wanted the whole cross product, meaning the vector product, we would need a direction as well. So I could say that A cross B is equal to, I want to keep the magnitude the same, but I want to send it in a direction that is perpendicular to both of the original vectors. To do that, I could multiply the magnitude by a unit normal vector. N stands for normal, which means perpendicular to both A and B. Now we use a positive unit normal vector if the vector is coming out of the page. If it was going into the page, we would use a negative n hat. And I should mention, this formula is for if we have geometric vectors. If we have algebraic vectors, we need a different formula that looks complicated, but I'll do an example to show you that it's actually pretty easy. I'll jot that formula down now for you. And now let's go ahead and do an example where we use each of those formulas. In this first example I've made, it asks to find u cross v, and then it gives us two geometric vectors. So we'll be using this formula right here, which tells us to multiply the magnitudes of the vectors times sine of the angle between them times a normal unit vector to send it in a direction perpendicular to both of the original vectors. So if I follow that formula for this example, u cross v would equal the magnitude of u times the magnitude of v times sine of the angle between the two vectors, which is 40 degrees. That would give me the magnitude of the cross product, but I want the whole vector cross product. So I need to send this in a direction perpendicular to both of those vectors. If I follow the right-hand rule, laying my right hand along u and curling my fingers towards v, my thumb will be pointing out of the screen or out of the page. So I need to multiply this by a positive n hat. And then an approximate value for this would be 385.7 n hat. Or instead of writing n hat, you can say out of the page. Let's try another example. In example 2, we're finding the cross product of two vectors, but those two vectors are given in their component form as algebraic vectors. In order to find their cross product, I'm going to have to follow this formula for finding the cross product of algebraic vectors. In order to find the difference of all of these products to get my three components of my cross product vector, there's a format I can rewrite these vectors in to make those calculations quite simple. Each of these vectors has three components. They have an x, a y, and a z component, because remember cross product, we need a z component because cross product can only be done in 3 dimensions. In order to do the cross product, I'm going to write the components of each of those vectors underneath their corresponding vectors in a very specific order. The order is second component, third component, first, and then second. If I sub these components into their proper spots down here, I can now find my cross product vector. To get the x component of my cross product vector, I need to do 3 times 6, which is 18, and then subtract the product of 2 and negative 5, which is negative 10. That gets me the x component of my cross product vector. To get the y component, I do 2 times 2, which is 4, and then subtract negative 1 times 6, which is negative 6. And then lastly, to get the z component, I find the product of negative 1 and negative 5, which is 5, and then subtract the product of 3 and 2, which is 6. And then if I simplify each of those components, I get the vector 28, 10, -1. And this vector is perpendicular to both vector A and vector B. So let me zoom out so you can see everything we did for cross product. And let's move on to the next part. Must know number 7. How to write the vector equation of a line. Let's say we have a line. I'll label it with L for now. A vector equation of a line is an equation that describes the resultant vectors that start at the origin and end at a point on the line. That equation often looks like this. We say vector r, the resultant vector, equals the sum of two things. Vector r0, which is a position vector, plus t, which is a scalar, multiplied by vector m, which is a direction vector, which is a vector parallel to the line. So let me define those for you, and also give you a representation to help you understand why this format of an equation could define a line. So vector r0 is a position vector to any point on the line. So I'll sketch a sample position vector. It just has to start at the origin and finish at some point that's on our line. The next part of the vector equation is vector m. Vector m is a direction vector that is parallel to the line. So I'll also sketch a vector that's parallel to the line. Now the key thing with this equation is that I need to add any scalar multiple of that direction vector to my position vector, and the resultant will be at some point on my line. And remember, multiplying a vector by a scalar can make it shorter or longer, or send it in the opposite direction if it's negative, but it will still be parallel to my original vector m. So I'll add a scalar multiple of this vector to r0 by drawing it tip to tail with r0 up here. Now, because these vectors are tip to tail, the resultant of adding r0 plus the scalar multiple of my direction vector is going to go from the tail of the first vector to the tip of the second vector. And notice this resultant vector goes to a point that's on my line. And no matter what scalar multiple of my direction vector I used, the resultant vector would still go to a point on the line. Let's now try an example where we calculate the vector equation of a line. This example says, write the vector equation of a line that passes through each of these 2 points. To write the vector equation of a line, the two most important things I need are the position vector and the direction vector. The position vector, r0, is a vector that points to any point on the line. So I have 2 points that are on the line. I'll choose a vector that points to point A. That would be the vector 4, -3, 1. To find the direction vector, I need a vector that's parallel to the line. So I'll use the vector that connects these 2 points together. That would be the vector AB or BA. I'll use vector AB. And when finding a vector that connects 2 points together, you do the coordinates of the point at the tip of the vector minus the coordinates of the points at the tail of the vector. Always tip minus tail. So to get the x component of vector AB, I do the x coordinate of B minus the x coordinate of A. 2 minus 4 is -2. The y component of my vector, y coordinate of the tip minus y coordinate of the tail. -3 minus -3 is 0. And then the z component of my vector, z coordinate of the tip minus z coordinate of the tail, 7 minus 1 is 6. And with any direction vector, we want the simplest direction vector as possible. So we need to reduce this vector by removing a common scalar from all 3 terms. I noticed that I could divide out a -2 from all 3 terms, and that would leave me with the vector 1, 0, -3. So I'll use this vector, 1, 0, -3, as my direction vector. So the vector equation of my line, we could write vector r, the resultant, equals, or the way it's more commonly written is vector x, y, z, which stands for our resultant vector, equals the position vector, 4, -3, 1, plus a scalar multiple of the direction vector, and we'll use the reduced version, 1, 0, -3. And then no matter what scalar I subbed in for t, if I were to do this vector plus any scalar multiple of that vector, the resultant vector would be at a point on my line. And as a bonus for this section, you should also know what the parametric equations of a line are as well. To write the parametric equations of a line, You just separate the resultant vector into its x, y, and z components. To calculate the x component of the resultant vector, we would do 4 plus t times 1. The y component is negative 3 plus 0t, so the y component is always negative 3. And the z component is 1 plus negative 3 times t. So those are the parametric equations of the line. Must know number 8. How to find the equation of a plane. Now, a plane is just a flat surface that extends infinitely in all directions. And we can write the equation of a plane in two different formats. We can write the vector equation of a plane or the scalar equation of a plane. Let's start with the vector equation of a plane. I'll start by trying to draw a diagram that shows you a plane. So I've got my three-dimensional Cartesian grid, and on here I'm going to try and draw a depiction of a plane. To write the vector equation of a plane, it's going to look similar to the vector equation of a line. It's going to be a resultant vector that points to any point on this plane. I'll call it vector x, y, z. And we get it by starting with a position vector, r0. And to that, we need to add scalar multiples of two different direction vectors. So plus t times direction vector 1 plus s times direction vector number 2. Let me define for you what those vectors are, and then show you in this diagram so you understand why the formula makes sense. r0 is a position vector that starts at the origin and goes to any point that's on this plane. So I'll start by defining it, and I'll draw a position vector to any point on this plane. And then m1 and m2 are both vectors that are parallel to this plane, but are not parallel to each other. So I'll show you what that looks like. I'll draw one direction vector, which notice it lays on the plane, so it's parallel to the plane. And then I'll draw another vector that lies on the plane, but is not parallel to the original direction vector. And notice if I were to add these three vectors together, since they're all tip to tail with each other, the resultant would go from the tail of the first vector to the tip of the third vector, which is a point that's on the plane. And by varying the scalars that we multiply by these two direction vectors, we can get to any point on this plane anywhere we want. Next, let's talk about the scalar equation of a plane. The scalar equation of a plane, I think, is a little bit easier. It takes the format ax plus by plus cz plus d equals 0. Now, to explain what all those parameters in that equation represent, let me first sketch a plane. And I'm also going to draw a vector that is perpendicular to this plane. We call that a normal vector. If it's perpendicular to the entire surface of the plane, it's called a normal vector. And why that normal vector is important is because the components of that normal vector correspond to the a, b, and c values of the standard form equation. So I'll make a note of that here, where the normal vector, vector a, b, c, is perpendicular to the plane. And now let me make a bit of room and we'll do an example. This question says determine the equation of the plane that passes through these 3 points. We'll start by finding the vector equation of the plane, and then we'll also do the scalar equation. To find the vector equation, I need a position vector, and that's a vector that goes to any point on the plane. I'll make it go to point B, but any 3 of the points could be chosen. So I'll use my position vector as the vector 4, 6, 2. And then I need 2 direction vectors that are parallel to the plane but are not parallel to each other. My first direction vector, I'll make it the vector that connects point A to point B. To find vector AB, I do the coordinates of the point at the tip of the vector minus the coordinates of the point at the tail. 4 minus negative 3 is 7. 6 minus negative 1 is also 7. And 2 minus negative 2 is 4. And then I need a second direction vector. It can't be parallel to this one, so I can't use vector BA, so I'll connect 2 different points. How about point A to point C? Once again, the coordinates of the point at the tip of the vector minus the coordinates of the point at the tail. So I can now write the vector equation. It equals my position vector plus t times my first direction vector plus s times my second direction vector. And no matter what you chose for t and s, the result would be a point that's on the plane. Let's also find the scalar equation. To find the scalar equation, I need a normal vector, a vector perpendicular to the plane. Well, I know these 2 vectors are both parallel to the plane, so if I did the cross product of the 2 of them, it would generate a vector perpendicular to both of them, which would be a vector that's perpendicular to the whole plane. So my normal vector is going to be the cross product of my two direction vectors. And when doing the cross product, underneath each of these vectors, I follow the order of writing the second component, third component, then first, then second. So underneath M1, 7, 4, 7, 7. And underneath M2, same thing. Second component, third, first, second. To get the x component of my cross product, I do 7 times 3 minus 4 times negative 3. 21 minus negative 12, that's 33. And then the y component, 4 times 8, which is 32, minus 7 times 3, which is 21. That gives me 11. And the z component, 7 times negative 3 minus 7 times 8. That's negative 21 minus 56. That's negative 77. And this normal vector, we want it to be as simple as possible so we can reduce it. I could common factor out a 11 from all three terms, which would give me 3, 1, negative 7. This vector is still going to be perpendicular to the plane. It's just shorter than that vector. So I'll use this one as my a, b, and c values in the scalar equation of the plane. And remember, the scalar equation looks like ax plus by plus cz plus d equals 0. So I can replace a, b, and c with 3, 1, and negative 7. And all we have left to do is solve for the d value. And I can do that by subbing any point I know that is on the plane in for x, y, and z. If I scroll up a little bit, I know that any of those 3 points are on the plane. I'll use this one, the point 4, 6, 2. So back into this scalar equation, for x, y, and z, I'll sub in 4, 6, and 2. And then to solve for d, I have 12 plus 6, which is 18, minus 14, which is 4. Move it to the other side, and I figure out that the d value is negative 4, which means my scalar equation, I sub in for a, b, c, and d, which would give me 3x, plus 1y, minus 7z, minus 4, equals 0. And there's the scalar equation of that plane. Must know number 9. Finding the intersections of lines in 3-space. Now, in 2 dimensions, if 2 lines are not parallel, they have to intersect at a point. But in 3 dimensions, if 2 lines are not parallel, they might intersect at a point, or they might not even intersect at all, meaning the lines are skewed. So let's do an example where I give you 2 non-parallel lines, and we see if they intersect at a point or if they're skewed. Let's find the point of intersection of the following lines if it exists. So upon inspection, I noticed that these 2 direction vectors are not scalar multiples of each other. Therefore, these lines are not parallel. What we do to figure out what scenario we have is we start by writing the parametric equations of these lines. So I need to break each of the resultant vectors into their x, y, and z components. So for line 1, the x component is equal to 5 plus 1s, y equals negative 4 plus 2s, and z equals negative 2 plus 3s. And then I'll do the same thing for line 2. And now I want to know, is there a single point that satisfies both of these equations? So can I find an s and a t value that gets to the exact same point? What I'll start by doing is setting the x's equal to each other, setting the y's equal to each other, and setting the z's equal to each other. And now let me simplify each of these equations that I've made. I'll get the constant on the left and the variable terms on the right for each of them. And now my goal is to see, is there a value of t and s that satisfies all 3 of these equations, meaning that their x, y, and z components will all be equal to each other. To do that, I'll start just by picking 2 of the equations. I'll pick equation 2 and 3. And with those 2 equations, I'll solve for what values of t and s satisfy those 2 equations. I'll use the method of elimination. So I'll stack the equations on top of each other. And then I notice if I were to subtract the like terms in these equations, the t variable would eliminate. I would have negative 1 equals s. And then I'll take that value I got for s and sub it back into either equation 2 or 3 for s, and then solve for t. I'll sub it into equation 2 for s. If I solve this equation for t, I'd have t equals 2 plus 4, so t equals 6. So this value of t and this value of s satisfy these two equations. Meaning, if I were to sub those values into the vector equations of the lines, it would make their y's and their z's be equal to each other, but I don't know if it makes the x's equal as well. To check that, we have to put both of these values into the equation we made from the x components, equation number 1, and see if it satisfies equation number 1 as well. So I'll do that check up here. So I've separated equation 1 into left side and right side. I'll sub in my value of t, which is 6, and my value of s, which is -1, and I see that the right side of the equation becomes 13, which is not equal to the left side of the equation. So that means that if I were to use these values of t and s, it makes the y and z of each of the lines be the same, but not the x's, which means the lines must not intersect. So we would say these lines are skewed. If when doing the check we did get left side equal to right side, that would mean that the lines do intersect, and then you could take your value of t or your value of s and sub it into either of your original lines and calculate your point of intersection. Must know number 10. How to find the intersection of two planes. If two planes are parallel, they could be parallel and coincident, so there's an infinite number of points of intersection. They could be parallel and distinct, meaning they never intersect. But what we're interested in for this section is if we have two non-parallel planes, that they intersect in a line. And I'll try and draw that for you. So I'll start by drawing two planes that are not parallel to each other. And if we're trying to find where these two planes intersect, notice there's going to be an entire line of points that are shared by both of these planes. And now let's do an example where I can teach you how to find the equation of that line that is shared by both of the planes. This example says to find the intersection of this system, which involves two planes. The first thing I would do would be to compare the normal vectors of these two planes. And remember, the normal vectors are just the coefficients of the variables. Those two normal vectors are not scalar multiples of each other, which tells me that the two planes are not parallel to each other. So I know that the two planes will intersect in a line. And to find that line of intersection, I start by trying with these two equations to eliminate a variable. So if I stack them on top of each other, which they already are, I could then subtract the equations from each other, and these x variables would eliminate. So if I subtract all of the like terms, I get -y plus 4z equals 2. And the next step is we assign a free variable. Of the two variables that are left, I'm going to let one of them equal t. So I'm going to say let z equal t. So basically I'm making the parametric equation for the z component of my line. I'm making it z equals 0 plus 1t, which means the x component of my position vector is 0, and the x component of my direction vector is 1. Now, I could have chosen any values for those two numbers, but to make this as simple as possible, we just choose 0 and 1, because then that simplifies to just z equals t. So I'll erase that, and if z equals t, I can then go back and solve for what the x and the y components would be equal to in terms of t as well. So if z is t, into this equation, I can let z be t, and then solve for y in terms of t. And then if I rearrange this equation to isolate for y, I would have y equals -2 plus 4t. So now I have z in terms of t and y in terms of t. I now need x in terms of t as well. So I can take both of these, sub them in for z and y in either plane 1 or plane 2. I'll sub them into plane 1. And now just isolate x, so it's written in terms of t. And I would have x equals 5 minus 5t. So these are the parametric equations of the line of intersection. Let me scroll down a bit and write them in the proper format. So I can say the line of intersection is, if I write the parametric equations, x equals 5 minus 5t, y equals -2 plus 4t, and z equals t. Or I could write the vector equation by taking the constant values as my position vector, so 5, -2, and 0, plus t times my direction vector, which is the coefficients of the t's, so -5, 4, and 1. So no matter what value you subbed in for t, you would get a point that is on the line of intersection, which means you would get a point that satisfies the equation of both of those planes. Thanks for watching. I hope that helped. Let me know in the comments what you want a top 10 of next.
Jensen Math!